Hello, how are you doing? Hi, everybody. How are you doing? Hi, Manny. So we have a few minutes before we start. Go ahead and check out your assignments and your notes for today. Sorry. I'm doing okay. Um, busy as usual.
Hey, Professor.
Hi, how you doing?
I'm good, and you?
Hanging in there. You know, it's this semester is just so crazy busy, and we're trying to finish up the data science program. And then I'm trying to launch a certification center and then apprenticeship at the same time, and then writing new classes. So it's been a little bit crazy.
What do you think about going back to campus?
Um, I every time I come to campus, there's always something to do. So it's gonna be busier than usual when we come back. Um, and hopefully everybody will get vaccinated so we don't have to put in all these barriers and things like that. But yeah, I gotta come over there to straighten up one of the computer room. We have equipment that was ordered and they came. So I gotta get district to come and tag them. I bought some switches and routers for my IT classes. But are you excited to come back on campus? Or are you guys like online?
To be honest, I'm kind of mixed about it. Like, I like certain classes online, like especially like the general ed classes, because
Hmm.
they're not really major requirements, right? Well, they are, but it's only to get to your associates. So I feel like those classes, I don't mind them being online. But like your major courses, like the mathematics and like physics and those kind of classes, I think I'd rather those in person.
Yeah, those are good to take in person, especially physics. Um, and then if you have Dr. B, I know that he mentioned something about retiring down the
Any
line.
class with labs.
Yeah, I know. Like biology, chemistry, those should be good for on campus. I have some classes that I need to make sure they're on campus because we need equipment. Like right now, I'm struggling with just testing stuff through simulator for my Python networking class because even though the virtual environment's okay, it just takes us, the student have to set it up and it's tedious. So if we have equipment, it's just so much better. But Mr. Barboza is gone. He's at Copper Mountain, and Dr. B is the one that teaches physics, right?
Yeah.
Yeah. So he's good. All right. It's 6 o'clock. It's that time. We have daylight savings, so we're a little bit earlier than usual, but so I want to let you know that on Thursday we're not going to have a live Zoom. I know some of you are in my class last night, so you already heard the announcement. I have to fly to Virginia early tomorrow morning. My grandmother passed away on Friday, so I'm gonna be there for her funeral. And the temple, she's Buddhist, they selected the day where it's gonna be on Thursday, so I couldn't move stuff around. But what I plan to do tonight before I pack up and get ready to go is to record your lab videos. I couldn't find the one that I used for the last semester. I might have deleted it. I don't think I uploaded to YouTube. I only used the Zoom and I switched Zoom account. So I will put up the video explaining how you would do the lab. If you have any question, you can send me an email. I will check my email periodically. I'm just afraid that the ceremony would take longer than it should, and because they're 3 hours ahead over there, I might not be able to get back to the hotel and teach your class, so I'd rather just have you watch the video, and then if you have any questions, we can address it, and then I'll come back and review some stuff the following week. So thank you for the condolences. She was 90, and we knew it was coming. I was just hoping that she would last until spring break, so I was planning to go over there during spring break anyway. But so on Thursday, if you do the lab, then you don't have to worry about it later, or you can just take your time to do it. What I'll do is I will have it due at the end of the week. So let's talk about what we have to do this week, and then let me get back into your class.
Oh, Professor, I was gonna ask if we're gonna go over the lab from last week,
Sure.
because we had a problem. I think it was the second one we did, where we had a R value, but the R
Mm.
value didn't really affect the code, if that makes sense.
Okay, we'll
Yeah.
take care of that. So I know there was some emails and messages coming in about testing the values. I think when I wrote the instruction, it was for the earlier version of the simulator where R1 didn't terminate out, and now on the new simulator, you see a bunch of, it's a -1. So I'll touch on that. I think our lecture is going to be mostly review. So, we'll get through it pretty quickly. All right, so let's talk about Unit 5. So after today, I'll post a video for the lecture that will go on to the Zoom page here. And then I will also post the lab recording. Just like how we do it in class, I will walk you through how to set up your lab. Just keep in mind that when you do your lab this week, when you work with the string, because we're going to output days of the week, it is space sensitive, so you have to line everything up accordingly. Otherwise, it's going to not show the entire string. So I just want to let you know that. So I'll remind you in the video. I will also post an announcement for the students who don't show up today, so that way they don't show up and there won't be a live session on Thursday. We will resume class the following week, and then we will work on additional stuff for LC-3. So for right now, I want to go ahead and address the notes and the assignments. So if you have those downloaded, please follow along. So this is the second part of chapter 5. And we have really gotten into the instruction in the last couple of weeks. But as you use it, you would be more comfortable with working with them. And so for today, we're going to look into more into data movement, and then talk a little bit about more on store. And then later on, we are going to get into the jump and the branching, like what we kind of talked about that in the last couple of labs. So for the data movement, as you remember, we would do a load. If you load to start, you have to store out. And in the later program, you would find that we would start with the store and then we have to load at the end. So they go hand in hand, and this is the way that we move data. So touching back to what you would see, let me open up my program here. In the last lab, for example. Okay. And in the last lab, you had started with the first exercise where you did the subtraction, right? X minus y, and absolute x minus absolute value of y. Now we started with an LDI, and we touched on this a while ago where we point to a location. So with LDI, what we're doing is we are loading the label to the register. And recall that I mentioned that register is never storing anything permanent. So what you need to do is you need to really associate that label with an address, okay? And so when we fill on the bottom with the label for X, we fill it with 3120. And then subsequently we put Y and so forth. So think about how you, when you write a program in C++, you declare a variable. Let's say I have int X, and we'll put that at the top, right? So for LC3, we would declare it on the bottom. We would say that this is a label, and the way it's filling, even though we put the value there, but it associates that with the location. Okay, I'm going to show you why. So when we run this program, we load it, okay, and we run the program. So before we run, we started the first line at the origination address, which is 3000. And on the left column, that would be your address, right? And in the middle, that would present you with the value. And then the binaries here would be the equivalent to what you would see in the value. So before we run this program, and in the program, we can test input to test if we have the proper subtraction. So if I set the value, I will go ahead and set it to 3120, which is where my X input is, right? So if we look back over here, that's going to be the first input, which is X. Then we're going to give it a value. And remember that everything is in hexadecimal. So I'm going to give X a 3. And we're going to apply. Then we're going to put in Y, which is at the next location, 3121. And let's give Y a 2. Okay. So before you start, you can set it. So now notice that before we run, all registers are 0. Then when we run the program, okay, you can simply go to the label itself, okay? So 3120, that's where my X is. You notice that the 3 gets placed in there, and then for X, and then the Y is placed in there for, so now it holds the value 2, and that's the binary equivalent. So when you set up the label, when you fill it, it associates that label with an address. And in C++, when we declare the variable, the compiler handle this part for us. We don't have to worry about it. But in LC3 or assembly, you have to tell it where that label actually exists. Because if you don't, it's not going to know where that label physically is located, and it won't be able to put in the data to that label. So earlier you saw that when we load the program, the label, the line for the X, when we declare that label, is different, right? And it uses that address. Let me show you that again. Okay, so when we jump down to the label X, look at this line. It's at 3022. Why is that? Because you started at 3000, and subsequently every single step, that's going to be an increment of 1. So by the time that we get to the label, which is the bottom of the program, this is the address where it would be able to find the instruction to execute for that label. It's not necessarily a label for, or it's not necessarily the address for that label. It is an address for the instruction to execute to create that label, okay? So don't mix them up, because I got some email asking to clarify this. So when we look at this address, when we load the program, the address on the left simply is the address for the instruction. Now, when we look at the field that we created for the label, that will be the location where it stores the actual value for the data. And so when you set, when you set your value, okay, when you set your value like this, if you jump to it, you would see that your value is placed there. Okay, so then the field address becomes the location where the data exists. The other address at the beginning, when you see the instruction, that's simply for the instruction to create the label. So it needs that address in order to establish the label. Then it's going to use the field address to be able to store data. Okay, so when you start filling all of these things in, and later on you would see that the program is not going to tell you where you would place the label. What if I wanted to fill it at 4,000? Sure, it will just be further down in the program, right?
Oh, Professor.
Sure.
So when we fill, that will be the address for that value?
Yes,
label?
that will be the address where the data is. So if I have X input, okay, for 3 actually is stored at 3120. That's for my X, right? And if I set the input for Y a 2, then it's going to store in 3121 because Y label is filled at 3121. Okay. And then subsequently, so when we look at the declaration of your your label, that will be where the data exists. So when you do the fill, that's where you're going to be able to find your data. Now, in C++, Java, the compiler, it handles all of that, right? It's given an an array of memory to work with, and it would dynamically put in the variable to a location. And when you assign the variable the value, it automatically stores it to that address. Now in assembly, you know that this is lower level, so we have to manually create these locations to put the data there. Otherwise, you don't have really a place to store the data, because if you revert back to the original instruction address, that's not where the data is going to go. That's just an address for the execution of that label, to create that label. Okay? So from this point on, you're going to start seeing a little bit more, and pay attention to what you're doing in your code, because the simulator, it's designed to give you the visual behind the scene, right? What the compiler handles. So at this point, what we're doing is we are really seeing what's happening inside the compiler, right? So when later on, when we write a stack, we actually see the value in, when we, push it in and when we pop it out. So, and it's good to really practice this and see. And if you wanted to make sure, you can actually do the step over like what the lab last week shows. So the BC counter here, it uses the address, right? Depending on the instruction, of course, but it uses the address to point to the next execution, what it needs to do, like, because it needs to associate, like, where is that instruction? Because in assembly, we basically put instruction in one location and data in another, okay? And we would tie them together, we would associate them, so that way we have a complete program. So the register, think of them as your middleman, right? It's a vehicle to get your data to an actual location, okay? And we move things back and forth. So you notice that my R1 is always F here. is because my program is complete. This is a termination signal. So in the previous version of the simulator, they didn't have this, but on the later version, they added this. So the value that was in R1, for example, X is no longer there because it's overwritten by the termination signal. So if you rely on register, there are some register would have the value because it's stored out. Okay, but some register, there are updated values that goes there. So think of them as temporary location. It's just, you know, a middle stop before we get to the actual permanent location of the memory. And we use it to move stuff around. Okay.
So back when we were talking about instructions and how they're represented in binary with all their operands, what does it mean when we use a label as an operand? What is it in the binary of the instruction?
So when you look at this, right? When you look at the fill 3120, when we fill that label, so we human would say that, oh, we're going to associate this label to this location, but the binary value, it needs to convert that to binary, and this is the equivalent of, so if you look at that line 30 hex 3120, this is the binary equivalence. Okay. And the way that we would do this is we would use this to tell the system that when it execute this instruction to create the label X, right? X is just a name for us, right? But what it does, we establish, we created this location so that way we can put the data there. So what it's doing is it's going to use the fill value to have that in here at this instruction line, and from there on, anything that you would move to X. So when you load X to R1 and anything you put into R1, it's going to tie R1 to that address. Okay, so it's going to say, oh, the fill is this at this binary, so it's going to point to that address to put all the data.
So when you use, say, the X as an operand in an instruction, when you assemble the program, it replaces that with the address.
Yes, that's correct. So when you do an LDI, let me jump back, okay? When you do an LDI R1X, we literally just use this as a placeholder, right? We just rename the 3120 as X. So that operand X really means it's 3120. So it's going to load it's going to load that address to R1. Okay. So, and then after that, we would update R1 and we would do and then the ALU would do the calculation after that. So at this instruction, what you're doing is you are loading the address to register 1. Okay, so that kind of lead us into the pieces that we need to talk about today. Okay, so let's really look closer with LD and LDI and LDR. So we already know that data movement consists of these. Okay, anytime that you load and store, that's data movement. And there are 4 types of load and 3 types of store. You have an LD, an LDR, an LDI, an LEA, an ST for store, an STR for another store, and an STI. And the I stands for indirect, ST is for direct, and STI is indirect. Same thing with load, okay? LD is direct and LDI is indirect. LEA is load effective address. This one, it skips the IR. So it just do memory to memory. And so if you start with the load, you have to finish out with the store, okay? Because you load the address, then you you do the calculation, and then your result needs to be stored back to the address that you originally loaded. Okay. Now, for the store, if we started out with the store, that means that we put the data at that location. You got to tell it to where to go to find that data. So you would have to load at the end. Okay. And the computer is very simple. It only adds, and it's only going to do what you tell it to do. So there's no complex at the low level. Okay. There's no complex things. All we're doing is just move data and add. That's all we're doing. Okay. So data movement requires two operand. We need to make sure that there's a source and a destination, right? So when we do an LDI R1X, that second operand is going to be the source, and it's going to load that to the destination, which is register 1. So now when you look at the load read the data from the memory register. And so when you do a load, you can also do an LD with the label. Okay, so you can do an LD R1 and Y. Okay, when you use an LD, then at the end, you just use an ST. So LD is a PC relative mode. You can load register into any of the general register from R0 to R7, but keep in mind, we want to be mindful of the register that we're using, especially when we're tracking them. And also there's certain register that's handling specific tasks. Okay. Then, so these are the steps that are happening when you're doing the LD. These are what they call the micro instructions. These are the mini steps within that load. It's going to calculate the new memory address. So whatever, if you do an LD, right, R1X like this, okay, what it's going to do is going to calculate the address of X, and it's going to add it to the PC, which is your program counter, and it's going to update the MAR. And MAR, its job is just to maintain a tracking system for the addresses that the computer, that the processor needs. Okay. Then the second step is that it's going to transfer the information from the MAR into the MDR, because when it gets to the MDR job is to do what? To deal with data. Okay. So the memory destination register, that's going to tell it how the register is associated with that address. Then the address would then transfer from MDR into the actual register, the registration register. And then in the case where if you're using branches and things like that. So what it does is it's going to actually set additional codes, and because it's all numerical value, it's going to be -0 or positive, and that's how it can distinguish the value. Okay. So these are the mini steps within LD. And for LD, how does it know the difference? It's just because the bits are different. 0010 is LD. Compared to LDR, it's 0110. So LDR is different than what we've seen with LD and LDI, in that it uses the base and the offset mode. It has the same functionality. It's going to do the load, but when it does the address calculation, it's going to do a base plus offset 6. Okay. So it's going to take, if you have a content in the register, it already has a value. It's going to take that value and it's going to add it to the address. So if I do an LDR R1, and a label, what will happen is it's going to take the address of the label, let's say in our case from the last exercise 3120, and it's going to add it to the value of that register. So in the back, the instruction is slightly different. Okay, the micro instructions, it actually has 4 steps in that it needs to load MIR, bring the address from MIR to MDR, bring the MDR to the DR, and then it actually update the CC. Okay, so on this one, it calculate the address or the offset, where in the other one, when it loads direct, it just bring the address to the actual register. Now for the indirect mode, which is what we've been using, which is LDI, same functionality, it's still gonna load. It's gonna load the memory address, and we mainly use label to pass address in assembly. So it's safe to say that if you are using label, a lot of times we do, right? All of the stuff is label oriented. Then we wanted to make sure that the address of that label is associated with the data that we're going to store. So the indirect mode, it's going to load from the memory, okay? Where the direct load, okay, it's going to load into the register, okay? All right, so let's answer the questions. Tells you to refer to the notes in the chapters. And we wanted to distinguish between LD, LDR, LDI, and LEA. So you can add all of the information that's in the notes if you like, but I just simply put that your PC, you can load value into the register using the LD and its PC relative mode. LD instruction takes the source label and store its address into the destination register. The source label must be within 255 lines of the LD instruction. So the example I put is LDR1 label 1. You have LDR. LDR, you can say that it's the same purpose of LD. LDR stores the source register's value plus the immediate value offset, and it stores it into the destination register. So if you're looking at this example, we're doing an LDR R1, R2, X1. So it's going to take this, it's going to add it to whatever that's in R2, and then it's going to put that onto register 1. Okay. So LDR stores the source of the register value plus the immediate value offset and put it onto the destination register. For the LDI, it treats the source register as an address, and it stores the content of the memory at the address in the destination register. So if you wanted to load label, you can do LDI or LD. However, LDI, right, the source register as an address. So if you're doing another register, it's going to use that register address. And it's going to store the content of the memory at the address of the destination. So it's going to put it on the register 1 here. So when we do this example, when we do an LDI R1 label 2, what will happen is it's going to take the address of the label 2, and then it's going to put that address to register 1 address. Okay. Where the LD, it would still take the address of label 1, but it puts it into the register. Then on the LEA, this is the immediate mode, and it does not access memory. It just loads the address to the register, and it uses register 0. Remember, LEA uses 0. Because 0 is first in the array of register. So I'll leave that on there for a minute or a few seconds. Okay, any questions with load? And next we're going to talk about store. Okay. So before we answer that, I'm going to take you to the next part of the notes.
Professor, so when we use LEA, it's more for strings, right?
Yes, a lot of times, the majority of the time for this class, you're going to see LEA being used with string for output string. And when you declare that string, what you're doing is what you establish a location where it stores the string. So it's gonna have, it's not gonna really use a physical address for it. So we didn't have to do a fill for it compared to the other one. It would have some kind of address information. Okay, so when you look at the details here, it shows you how each of those, the diagram for the LDI. Okay. So for the store, move content from the source register to memory. So when I say store out, that means that we're going to take whatever the content, the value from the register, and we're going to put it to the memory. So you can do an ST. And so you would do an STR1 and a label. Okay. So let's say we put label 1. We can do STR1 label. That means what? It's going to take whatever that was in the register 1, and it's going to put it onto the location, the offset of that label 1. Now, store is the only instruction that goes in reverse. Now, you notice the source comes first compared to the destination. Okay. So in the micro instruction, what it's going to do is going to look at the bit 0 through 8, this section right here. Okay. And that would represent the PC offset. Now it's going to add the value to the incrementing PC, which it increments by 1. So whatever is here, it's going to add it to the PC. And then after it did that, it's going to store it into the MIR. Then to acquire the content, it's going to bring the content, transfer the MIR directly to the memory. And then it's going to transfer the MDR to the memory, which is the data, right? So what it's doing is going to be able to identify where that is from the MIR, the actual address, the physical address, and then it's going to take the data content and it's going to put it to that location. So that's when you do a store. So in a store, if you're looking at the simulator, you also see other register like register 0 and register 7 being used. And then it's actually subsequently, it's gonna have to load. After it loads, it stores, it's gonna be able to bring the data to that actual location. Now for the STR require a base register, and it's going to use that to store the value into. And we would do a STR when we work with immediate value. Okay. When I put SR, that's just source register. Okay, so like we can put the R3. So if you're working with immediate value, okay, then that would be represented as hexadecimal, like you can have hex, I don't know, 4000 hex, whatever value that you like, you can put that there. And then it would take the source register and then store it to the location. We will have a 1 or 2 lab that will have this. So you will see. Okay. So when we look at the code, how is that different, right? ST uses label, STI uses label. STR is going to use an immediate value, like a hex number. Okay. For the STI, we touched on that already. So the example for the STI would be, you saw this in your lab, STI R6, right? And then we can have Y or Z. So for the STI, right, if we have a field address for Z, it's going to put that in and it's going to use that. So in this, that's where the address is, the bit 0 through 8. Okay, that will be your label address. And then what it's going to do is it's going to take the PC, which is your program counter. It's going to include that, put that into the PC, then transfer that to the MIR. And then from there, it's going to take the content address from the MDR, that's where your data is, and then put it to the location of the address. Transfer the content to the memory. Now in the STI, there are 2 addresses that are involved. The content memory address, which is the first address, and the second address is going to point to the data. So the data is being pointed to from another location. And that's the true difference between ST and STI, is that it's using 2 addresses in the STI versus the ST, it's only going to have 1. Okay. Then I already talked about LEA, so you don't need to. So here is my answer. For ST, move content from source register to memory. Your example would be STR1 and a label. I just put ADD R2. And it stores a value from the source label, or I'm sorry, it stores a value into the destination register. For the STR, it stores the value into the base register from offset. And your STR example is that we would do STR R0, R1, and a decimal 1 or a hex 1. So what it's going to do is it's going to take, right, your source register, it's going to add this with the PC increment. And then once it finished that, it's going to transfer that to the MAR. And then the MDR is going to be able to load or to transfer the data to register 0. So it stores the value in the source register, which is register 1. And your immediate offset can be used. So in this case, we have a decimal 1. Okay. If you do not want to use, if you not want to use an offset of number 1, then you can use like an actual address or a hex value, etc. Just take this line out. I don't know why I put that there previously. For the STI, we said that the content of the source register is stored onto the memory location. So we would have a label and we would have your register. So it's going to take the content of the register and it's going to put it to the address of that label. But really it's pointing from address to address in the back. So STI treats its immediate value source or the label as memory address. That's why it needs the fill, right? And it stores the value of the address into the destination register. So we would use the register address to point to the actual label location where it would have the data. That's when you store out. Any question? Okay. No question on 2. All right, you can find all of that information also from page 2 and page 3 of your notes. Okay, so let's do this one together. Number 3 asks you to write the instructions for the following exercises and answer the following question in each exercise. Okay. For A, we are going to load data from label count 1 into register 1. So you can use either. Okay, now you can tell the difference. So I put, if you can use LD R1 count 1 or LDI R1 count 1. The second one is an indirect load. And the first one is the direct load. So if you choose to use LD, explain to me why you would use LD. Okay. Or if you choose to use LDI, write down the reason why you would use LDI. It still fulfills the same purpose if you use one or the other. Just keep in mind that indirect load, we're using a memory pointing to another memory location, where in the the load, then we would load the address to the register. Okay, so explain why you would use either one or the other. And when you use the label, don't forget the fill. You can fill it wherever you like. Okay. So I normally, assuming that my program never reaches 100 lines or 1,000 lines, then I fill a little bit earlier in the program. Some developer, they would fill like at 4,000 because they expect that their program is going to be a lot longer, as we subsequently would have, the addresses starting at 3,000 and then going down. For B, we are to store data to register 2 from label HW. Explain why you would use ST or STI. Okay. So just like the other one, we can use ST or STI. So if you use ST, you can say STR2HW. We would store R2 content to the location of label HW. And when you're doing a direct store, what that will do is it's gonna access this address and store the content to it. Now for STI, you can do STIR2HW. You're using another address, the register address, to point to the location of the label with the R2 content. Sorry, one second. Okay. So hopefully after this session, you'll be able to understand a little bit more about data movement instruction. Then for C, we are going to load effective address to register 0 using label ADR. What must you specify in ADR before issuing this instruction in LC-3? So we need to do LEA-R0 ADR. Okay, and we would move data from the ADR label to register 0. So if you go back to the notes in the section where it actually talks about this, right? Load effective address, it compute the address and it saves that to the register. So load base address and store it into the destination register. And then it's gonna set CC. So for this, it asks you what must you specify in ADR before issuing. You have to specify the content or data in ADR. Understand? So earlier we mentioned that we are using string for most part. So what does that mean? You need to declare your string to that label, because what's the whole point of moving data if you have nothing, right? So you need to, another word for this would be you need to declare data in ADR label. Question? So LC-3 is not hard. It's just different, right? At its most simplistic level for programming. Because we're so used to higher level that we forgot, right? Or we don't know the simpler level. But if we understand what it is, we're able to use it, and it's a lot easier than you think, right? Once you see it, once you get it, once you know the functionality of the instruction, it's just very easy to use. Okay.
So when we were using .fill to put an address into a label and LDI, we were loading the address that we stored in that label. But when we were using strings and LEA, that was loading the address of the label itself.
Mm-hmm. Yes. You load the address of the label itself. Okay. And also, do I have to fill for this one? You think I have to fill for that one? Remember the first example that we've done? Hello world, did you have to fill?
We used string Z.
Mm-hmm. So what that will do is you don't need to have a fill, right? Because you don't have to specify what address it's using. It's just going to use that subsequent address, the incremented address that where it would be. Now, in the case where you have very large string, or you expect a very large string, right? What you should think about is how that would fit into your word size. Remember what I said about, well, what if you have a whole paragraph you wanted to output? Well, you can set up a block of address, where in that case, you can have a block word, and that would give it subsequent address consecutively in order to establish that offset. So the nice thing about LC3 is you don't need additional flags and things. It handles some of that for you. In other assembly languages, you have to set the flag, for in the case where it, so that way we don't have like buffer overflow and all different things. So every assembly language has its particular thing, right? And in this one, there's not, it's just what, 15 instructions, 8 registers, and then there are different category in the instructions, and we're pretty, it's all right. It's not too bad, easy. Okay. All right, so let's talk about jump. So jump allow us to move to different part of our code. We can jump, and jump doesn't have a condition like BRZ or BRN, right? You can just jump to a label. And jump works across many different assembly languages, okay? Some would say JMP like this one, some would actually you type out jump. So jump, it's always gonna take it. So when you tell it to jump, you can go from the top part of your program to the bottom part of your program if you want, before the data declaration. So in what happened is it's going to use the target address, which is the label address. And that is going to be the content of the register that would allow. So it's going to go to that target address, and that's going to happen here. Okay. Now compare that to a branch. an unconditional branch, which is a BR. BR instructions can only access, right, this range of addresses. Okay, so jump is a little bit higher in limitation or less in limitation compared to a BR. But BR will still get you, you can branch to a label and it will go there regardless. It's still going to fulfill the same purpose. But the limitation with BR is that you only going to be allowed this range, okay, before the instruction. So when you jump, what that will do is it's going to take the label address and it's going to put that into the program counter so it knows where it's going to execute next. The program counter job is to keep a list of the location for execution, right? So if you tell it to jump to label 1, well, it's going to take the address of label 1, put it into the base, take that base, put it into the program counter. And so from there on, it's going to execute the line, right? Or the instructions from that address and forward. Okay. So there's only one thing that's happening with jump. It's going to load the PC with the register content that was specified. And jump doesn't have limitation. So since register has 16 bits, the full address space of memory, the jump instruction doesn't have the limitation where the next instruction is executed must reside. Okay. So let's do, so we can jump to a register. So for D, we're going to jump to register 4. And all we're doing is we're just going to go to that location. Take the program and go to that location. You can jump to a label. So jump to a label and also branch to a label makes more sense to most developer because we would use that to navigate our program, right? We would say, okay, do this and then go over here and do that. Okay. And then come back to the middle later. But in this case, we're going to jump to register 4. So simply that's just the location.
So if you wanted, since jump requires a register, if you wanted to jump to a label, you'd have to load the address of that label into a register first.
You are correct, sir.
So LEA.
Well, you can actually, well, you can do a regular load with that, or an indirect load. If you do an indirect load, actually you can do a regular load because it's going to load that label to the register and then we're going to use that register to jump. Now, I think we're going to do one jump in one of our labs, if I remember correctly. When I taught Microsoft ASM, we did a lot of different jumps because Microsoft ASM uses C compiler and you can do more on the graphical user interface side a little bit. It's not very pretty, but it's still going to work, like menus and stuff like that. So when you look at like some of the executable, okay, I know that you can write executable using like C#, like, you know, the .exe, the installation file that, you know, the MSI stuff that you get when you install things on PC. Well, you can write it in higher language, but, you know, in the case where if you need to do like driver installation, a lot of the times you would see that developer would use assembly to do that. And it's such a small program that you can do it in assembly. I've done it with my class where they install like make it an executable and run it. So you can package it too. Okay. So next we're going to talk about a little bit about trap. I know I previewed it in your lab last week. So trap is a system service call. Okay, and when you look at your simulator last week, you saw some trap and a value. Okay, this is useful for getting data into and out of the computer. So when you're doing return, it's going to trap. Okay, when you end the program, that's a service call. That's a system service call. So that way it's going to terminate, right? So there are a lot of things that we already included in the program that requires trap. And so when you use trap, what it does is it calls for the service routine, and all that is a function that's built for the system. Okay? So you recall when we did a get C, right? A get C listens for the keyboard, it waits, right, for the character. Or when we use in, right? So when you have an input of a character from a keyboard, it uses trap vector 23. When you have an output, when you do an out, right, to display on the console, it uses trap vector 21. So when you do an out, this is happening in the back trap. And in the simulator, it would show you there's a trap, and that will be vector 21. When you do a halt in your program, it's a vector 25. Okay. And there are more, and we'll add more to it. So for now, you see a lot of these common trap vector, right? So when the subroutine is done, the program counter is set to the instruction following the trap. So when after the trap occurs, the next line, that the location of the next instruction, that address is loaded, is added to the program counter. So it's going to continue in execution subsequently. So when you halt in the loop, after that, it already knows that that loop is complete. It's going to go to the next line to be able to execute the next line. Okay. So when you think about your C++ program, when you run, when you compile your program, for example, if I'm doing a break or continue, those type of statement, right? Actually, there's trap happening in the back if you think about the assembly level. Because when you break, what does it do? It's going to go to the next line and it's going to try to execute the next line. So the compiler at the assembly level, it needs to load the next line instruction address and be able to pick it up there. There's no magic about it. There's got to be a mechanism that's built into the compiler for that. Okay. So here it gives you additional, like for trap 20, that's a get C, out is 21, puts is 22, 23 is in, and vector 25 is halt. And if you read on the right hand side, it tells you a little bit more detail. So when you do a get C, it listens for the keyboard for the character. The character is not echoed onto the screen. That means that it's not going to display it, right? It's just it's like your C in. So its ASCII code is copied to the register 0. The high 8 bits of register 0 is clear. Okay, so register 0 is dedicated for that, and it's going to store the ASCII value to register 0. So that's why when we have multiple input, we got to move it. We're going to move it out of register 0. Otherwise, it's going to get overwritten. And it will be translated to something else. For trap vector 21, it writes the character to register 0. And that happens from bit 7 to bit 0. Okay, here. And it's using that to show on screen. So write string pointed to register 0 to screen. So how does it know what to go to screen? Well, whatever's in register 0, that's what's going to output. The print for in, that's just going to give you the input. So print the prompt on the screen and read the single character from the keyboard. The character is echoed onto the screen. So the difference between getC and in is that getC is still a character, but it doesn't show on the screen compared to in. So that means that the ASCII code is copied into register 0, and then at the high bits of register 0 are clear. Halt, just halt execution, it stops. Okay, so here it talks a little bit more about what register 7 is doing. So if you look at your simulator after you run your program, you will also see register 7 somewhere in your simulator, usually like near the middle. It will show R7 and then an RET. So that allows it to return the service call. Okay. So with that, the content goes to the MDR and then it gets transferred to the program counter. That's how it's knowing it's going to be able to pick up for the next. Okay, any questions with trap? So for halt execution, that will be the halt instruction. And we would use trap vector 25. Make sure you know your trap vector for the final end quiz. Okay, so let's work on 4 and then we'll talk about branch. Let me go slow. All right, 4. We are going to clear register 1. So we're going to do an AND R1, R1, and you can use hex 0 or decimal 0. That's up to you. Same. Okay, so for A, we're going to do an AND R1, R1, 0. Now we're going to have R2 is going to be equal to decimal 3. So we need to add it. Okay. Add R2, R2, 3. Now what you can do is you can do an LDR with it, but I advise against it because LDR associates address with it. But LDR does load immediate value from the, so you know, if R2 is clear and if we do LDR R2, R2, 3, what will happen is it's going to take the 3, add it with whatever that's in the register 2 and then put it on the destination. But it's better that if we do the add. So at this point, we would add 3 to register 2, assuming that it has nothing to begin with. Then we want to do a copy. We talked about this already. So we would do an add R2, add R3. Did I have it in reverse? Oh, same, yeah. Add R3, R2 to 0 because we already put 3 into R2. So now we're going to copy that onto R3. And so we would have R2 is equal to R3 in this line, which means R3 contains decimal 3 subsequently in our exercise, right? So when you add the 0 with 2 register, you copying them because, you know, if you do the manual addition in binary, you're going to see when you add the 0, it's the same. Then for 4D, R4 is 9. So we simply add 9 to R4, add R4, R4, 9. So R4 is equal to 9. And then for E, we are going to add R2 with R4 and put it back on R2. So we would do add R2, R2, R4. We add the values of R2 and R4 together. So R4 is 9 and R2 is 3. So we should have a 12, decimal 12 in R2, or, you know, in our simulator, it's going to give us a hex equivalent. Then for F, we are going to add R3 with R4 and put it back into R3. So we'll do add R3, R3, R4. And recall that we copy R3 from R2. So R3 has a 3 and R4 has a 9. So R3 at this point is also decimal 12. Okay, so for the final exam, you are going to be given snippet of LC3, and you have to tell me by the time that you finish those lines, what is in register 1 or 2 or 3 or 4, etc. I'll ask for the value at that register, and you have to know. So you got to follow it. Okay. Any question? Okay. For G, we're gonna do an if, so we have to branch. If register 2 is 12, go to R3. Now there are several ways to do this. So so what happens is we need to make sure that this line is above the branch. Otherwise, it's going to check for the register 3. Okay, so let me do this. Okay, so we got a branch like right below the register, the destination that we want to check. Okay. Now, if you wanted to check register 3, that will be easy because register 3 was there. Okay, let's do that instead. I'm sorry. Let's change this to register 3. And then we're going to go to R2, go the other way. So if register 3 is decimal 12, then go to register 2. So we are going to branch positive right after this line, because this line will allow us to check for positive number, which is 12. Okay. Now, if you really want to check it for 12, what can you do? This is what you can do. Okay. You can subtract 12 from it. Okay. So if you really wanted to check for 12, you need to compare 12, meaning that you need to subtract 12. So we can do an add with the 2 complement, and then if it's 0, then we can jump. Okay. So in this one, I got lazy, so I just do a positive check. So I just do a BRP to positive, and then under the positive label, I have it jump to register 2. Okay. But you know, if you really want to make it work accordingly, you need to check. You need to subtract 12. And if it's 0, then you can jump. Okay, so we simply branch for positive if register 2 is 12. Now, if we branch for positive, I mean, 5 would be positive, 10 would be positive. So we're not really checking for 12, right? So the proper way is to subtract 12. But like I said, I wanted to minimize the extra steps, so I just put branch positive. Because 12 is a positive number, it's still going to branch. It's going to go to POS, and under POS, I have it jump to register 2. You can jump to a label. Now, if I want to just force it to branch regardless, I just have it BR POS, and it's unconditional, so it's gonna have to go, right? And that's more of like a cheating way to do it. That's not appropriate. But if you really wanted to force it to go, then you can do a BR. But in this case, we just check for positive. And then we end the program, .end. But you know, before that, you would do the declaration of data and all that good stuff. And if you want, you can halt it somewhere in between. So does BR set register 7? No, I think it does. Let me see. Let me double check on that. I don't remember that it does. Did I run this already? So here is that. Here's the store out. There's the load for 0. Yeah, I think it uses register 0. Because this is like when it finishes right here, when it returns a service call, and then it ends with the -1. With the halt. So no, we don't use register 7 for the BR because it uses flags. So it's gonna require like 1 or 2 bits for the flag for that. So no. Okay. Do you have any questions for me? Okay, so by this point, when we look at the pseudocode, we should know how to do this, okay? Because, you know, in future program, I'm gonna move much faster where we have to write like a while loop and other things. Your program's gonna get longer. I'm still gonna walk you through the program, but at the same time, I'm not gonna go back to the very basic because we have to move forward. So practice. If you're not sure, go back to your assignments and then be able to look at your code or how to write it out. right? And then go back to the exercise that you couldn't do before because you didn't know how to copy or you didn't, fix those programs and get it to work. And that's the whole point of, improving your skills. Okay. And you don't have to make it exactly like my program, but if you're still able to achieve what you want to achieve, you'll be fine. Okay. All right. Because at Cal State San Bernardino, when they teach this type of class, they only go into digital logic. You have to look at the lab manual and figure it out on your own. Even the TA, they only walk you through like the first tutorial program, and then you're gonna have to write your own instructions. So, okay. Questions? There were some concern about the prior lab, right? Like number 2, I think I heard earlier. But before going into that, I want to kind of preview this week lab, and then I will have a recorded video, but for those of you who are whiz at this is the time that you can just kind of get the preview and then write your program. Okay, so let's talk about lab. So in this lab, you are going to output the day of the week based on the user input. If the user press 0, okay, it's going to give you Sunday. Okay, so what we have to do is we're going to set up an array that's going to store the values. And in C++, if I was to do this in C++ or Java, I would do, right, a 2-dimensional array, right? That's pretty easy. We would associate the number 0 with the Sunday, Monday is 1, Tuesday is 2, and so forth. So there's 7 days of the week. So we're going to ask the user to input a value. So we are going to do an LEA string and then output this, right? We're going to put it, and then we're going to do an in, then we got to convert it from ASCII to hex, right? We have to do the offset. And then after that, what we're going to do is we are going to correlate what this is to the actual string. Okay. Now I know when you look at this program, you say, oh, C++ piece of cake, right? So what you need to do is when you work on this program, you got to break it down into pieces that's digestible in LC-3. Otherwise, it's going to feel very overwhelming. Okay. So here it explains that when you record an input, you need to ASCII convert it. We've been doing that. Okay. And then I'm going to show you the technique that's a little different than what we've been doing. And then when you output the string, remember that it's null terminated, and then we would use the strings to load the string into the memory. So here it talks about string, and the thing that you wanted to point out is, or I wanted to point out is when you have a strings like Sunday, when you're looking at the actual string itself, right? It's gonna have, string is an array of character. So it's going to start with the S. Let's say that it starts at 3100. The S is going to be at 3100. The U is going to be at the next one, at the next one, at the next one, at the next one. And then it's going to be null terminated. So be careful with white space, because if you throw in something, if you misalign it, it's going to throw off the character. It's not going to show it. Okay. Because subsequently we would use each character as one address, at one address. Okay. Okay, so then this, it talks about puts, it talks about trap, And then reading input, we've seen this before. So in this one, this is how we're going to ask you convert it. We're going to subtract 48. And the way that we subtract 48 is we subtract it 3 times. 16, 16, 16 to get the offset. And so when we subtract it, and then when we want it to output, we got to convert it back. But we're outputting string, we're not outputting the same number. So we simply subtract it. Okay. So here it talks about why we need to do it in, you know why we subtract it 3 times? Why do we subtract it 3 times and not 1 time? Why can't I just go add R3, R3, negative 48? Anyone know? Why can't I put negative 48 here and not have to do it 3 lines? Because it is larger than 5 bits. That is correct. Okay, very good. You guys remember when you try to add the hex 4D or whatever 4E, right? It's too large. So because negative 48 would overflow the 5 bits, right? If you want to do the conversion, you can convert. What is 48 in binary? If it's more than 5 bits, then it's not going to fit. So we have to make sure that it fits the 5 bits. And in order to fit the 5 bits, we got to do it 3 times. Okay, so subtract 48, 48, 48. And after you learn this, you're like, oh my God, why were you teaching me how to do the 2's complement? Well, you have to learn how to use 2 complement, but you can, LC3, you can do it this way. Okay, other assembly, you got to use 2 complement only. So we're going to do the negative decimal this way. Okay. So once you subtract the, yeah.
Oh, the biggest number we can use was 31, right? Or was it 32?
We were using offset 30, but that's when we convert numbers to numbers. In this one, what we're gonna do is we're gonna convert it to the hex and then correlate that hex with a string. Okay, so the offset of this will be 48. So with that, if you subtract 48, your ASCII value is at 0. Okay, and then so after that, what you convert it to the offset. Now, I'm going to say this now, and I'll say it again in my video that I'm going to put up. Make sure that we line everything up straight. If you're off by 1 space, you're going to cut off your Saturday and your Wednesday and the one with the more characters. Okay? So when you put in the quotation mark, make sure that they are all lined up, the first letter all line up, and all of that. Because if you just type them next to strings and not line up, you're gonna have a hard time outputting. So when you output and it cuts off, you know, it will say like Earth Day instead of Thursday. It's because you misaligned it. Okay. So that's how you troubleshoot. Go back, right? Fix your spacing, save the program again, assemble, reload, and see what it does. Okay. All right. So here it gives you the formula on where the address of the days would be. Okay. So what it does is we're using an index, and we are going to associate the index with the day, right? Remember? And we are going to multiply it by 10. So the address of the day is the address of the label days. And why is it 10? Do you know? Look at the days. How many characters do you have? Okay. Why am I giving it 10? Remember that the string is an array of character. So how many characters in the days that has the most character, which is Wednesday? If you count it 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is because it's null terminated. So what we're doing is we're setting up the address array for the character that would be spelling out the day, right? The character that we can use to spell out the string for the day. So because it requires the one that had the most character is Wednesday, we would allocate 10, right? 10 for all 10 characters to represent Wednesday. Okay. And then the other ones that have less character, that's okay because it will just be blank space. Okay. So when it does that, it's going to establish, right, a slot for each of the character, and it's going to use that to display SUNDAY. Okay. So for your future project, if you have the user input a string, you have to think about where it's going to store that. You first have to move it from register into a location, and then we want to put in subsequent location in an array to store those characters so that way it would show up as a string. Okay. So this 10 here just represent 10 slots for the characters. And then they give you the snapshot, which is the loop and the display. So in this one, you would see a for loop being used, right? So if you think about a regular program when we have to iterate through, right, to like indexes, you use index to be able to show something or access that index, you would normally implement a for loop. Okay. So to be able to access the index, we would have to loop through. And when we loop, we simply use the label and we would branch. Okay, so in this case, when it gets to 0, it's gonna go to the display, and display, it's just gonna output it onto console. So what we can do is we can subtract it. If it's equal to 0, it's gonna show. And then after that, it's gonna go to the next day. Okay. And then so on. And as we loop through, we got to count down. Okay, so our counter, it's going to go 10 and then less, right? 9 and 8 and so forth. So we got to loop through the characters for the 10 slots. Okay, so we count it down by subtracting 1. Okay, so what I'll do is on the next video that I put up, I'm going to walk you through the program. You're going to build that program. You're going to write it. You're going to assemble it. You're going to load it. And then you need to give me the screenshots. Okay. And I want you to test it. 0 through 6. Are you getting Sunday, Monday, Tuesday? Make sure that it outputs the whole string. Okay. So I want you to test Sunday. I want you to test it with a 4, a 5, and a 6. Right? Friday, Saturday, Sunday. Or Thursday, Friday, Saturday, Sunday. Okay. Then describe how you debug the program. Okay. And what challenges you come across. Every semester that when I write this program, some students always have it misaligned and they ended up having to fix the program. And that's okay. Okay, so if you mess up and you misalign it, go back, fix the alignment, and rerun it. You should be fine. Okay. Now, the second part is hard. I'm not going to give you the code for this. I want you to think about it. Okay. So for a few years now that I teach this class, last year I had 55 student class for assembly. Okay. 15 turn in successful program for this, but it is achievable. You can solve it. If you can solve the other one, you can solve this one. It wants you to write an assembly program. You can refer to the last one, but instead of the day of the week, I want you to use the month of the year. Okay. Now the challenge is going to come in when you need to record 2-digit. Because remember that when we ask the user input 0 through 6, right? That's easy. It takes the 6 and put it in. But how do you handle anything above 9? Okay. So I want you to think about it and do it. If you successfully do this, I will give you extra credit, 30 points. Okay. But if you attempt and you don't get it to work, I still want you to turn it in. Okay. I want you to screenshot your code and I want you to turn it in. If you give up, which you shouldn't, I still want you to turn it in because I wanted to see how far you get. I can assess your understanding of the program and your logic in that, but I want you to try to think about it. How do you take the value of the input and interpret it and make sure that it's going to fit the 12 months in a year? Okay, because the first part looks just like the other program. That's easy. You can edit the other program and fill it in, but in this one, it goes beyond 9. Okay, so think about how you would use 10, because even with input, the user can't type in 10, right? It's going to record 1 and 0. So think about how you would record multiple input, because that's going to help you with your project in the future. Okay, so I want you to put forth your best attempt to do number 2. And even if you don't get it run, successful, I still want you to turn it in. Okay? All right, so that's the lab for this week. But I will, in the video, I will walk you through the steps for doing number 1. And then after that, right, after next week, after you turn in the lab, I will go over the program with the month successful. I've had many students turn in many different solutions and most of them work, right? I looked at different approaches. It's very cool because I see how they think, right? Oh, I'm going to handle it this way and solve it. So I like for you to see if you can solve it. Okay. All right. And don't just Google the solution because that doesn't help you. Okay, so if you successfully built the program, test it, either way, give me the screen capture. All right. So I want you to beat last semester because last semester 15 of them turned in. So I'm hoping you guys have more, okay? Because I know that you're very smart. You can do it. Okay, any question with the lab? I kind of preview it so you know what to expect. And it gives you time to think about how you solve it. Okay, let's talk about last week lab now, because I know that you had some questions on that. So I addressed the things with testing the values for number 1, right? And then for number 2, I had helped you write for the program. Pretty sure I did for most part. We gone through and wrote out the code. Right, I even color coded it. So to test the number 2, you just simply have to do the same thing. So go to the fill location, set the value for P. You can give it anything you wish, and then set the value for Q. And then because RES, the way that you store out from RES, if you look at the criteria for the program, how do you know if it gives you the right result, right? This is RES. You're going to go to 3202. And if you see a 2 added to that value, so you got to set the RES value as well in order to be able to add. So you have to set 3 values. Okay. So if I set here is 0, then if it shows up a 2, then I know that P minus Q is a positive number. Okay, so that's how you can check. Okay, so testing it is very similar to number 1, but in this case, you have to have 3 values to test. Then for number 3, did we finish number 3? I don't think we did, right?
We never finished it.
Okay. So for number 3, do you still want to finish it for me to help you finish it, or do you want to try on your own? I think I didn't require it, but I told you to work on it.
Professor, for the number 2,
Mhm.
do you mind running it so I can show you what I was talking about earlier?
Okay, let me have you share your screen. Do you mind sharing your simulator?
It would be better if I just explain it to you when you run it.
Yeah, I don't have the program on this computer.
Oh no?
I have it on another computer.
Then yeah, I
Give me
can
1 second, actually. If you wanted to run it, you can show, but if you give me a minute, I should be able to copy and paste it over.
Okay.
You said number 2, right?
Yeah.
Okay. Let me close out some of the white space here real quick. Okay. I had an SCI and a hop. I just had it tab in from Microsoft Word coming over to the editor. It's not very pretty. So let me fix the look of it real quick. Okay, so we're gonna go ahead and do a save as. Next to the ISM. Let me assemble it. Okay, so let's see. Okay, so here's the program. We're gonna load it. Okay, and then run it. But before you run it, you have to set value. So I can go to, let me look, 3200 and 3201, 3202. So we would need to go to hex 3200. That's going to be your P. So let's say we give it a 9. And then for the 3201, that's your Q. So let's give it an 8. And then 3202, I'll give it a 0. Okay, because so if we test this, right, based on the criteria, oh, wrong one. Based on the criteria, so if we do 8 minus or 9 minus 8, that should be 1, that's greater than 0. And since we set the RES as 0, then we would see a 2. Okay. So once we apply this, we can jump and make sure that they're in the location. So 9, 8, and 0. Okay. So let's see, 3200. So I'm off here. Let me see. 9. Oh yeah, so it's 3. That's right, because it's gonna take the value plus. If it's greater than 0, subtract 1. So I set it at 0. It's gonna add the 2. So I'm
No,
off by 1.
no,
I'm off by 1.
you're correct. Because what the program does is that it takes P minus Q and then it takes that value and then it
And then
adds.
add it.
Yeah.
Yeah.
But the thing with the problem is that, like in the equation that we set up, like what we're going around, it's either P minus Q, right? And then if that value is there, then we're gonna add 2 or we're gonna subtract or we're gonna add 1, right? But if you think about it like in an equation way, if we have P minus Q equals R and then we're gonna add some value to that, R can't be set to any number. So it's gonna be initialized at 0. So no matter what value you set for R in the LC3, it's just going to do the P minus Q and then it's going to add 2 or subtract 1. That's why I was kind of confused while you were asking us to set values for R.
Well, you have to set value for R to actually check, because if you say that it sets it to 0, well, why would it set it to 0? Because if you store it out to a location, if you give it a value, you should still be able to test it. You see what I mean? I don't think we understand each other though.
Can you try and rerun the program and see if you get 3 again if you change the R value?
So reinitialize the machine, reload the program. Okay. So you're saying I shouldn't set the value for R?
Set it to a number besides 0.
Okay. Now let's say I do P, let's do 1. Okay. And then
Professor, can you use 9 and 8 again so we're for sure that we
okay. Good idea. So we would do an 8. Okay, and then 3202, I'll give it a 1. Right?
Yeah.
Okay, so now let's run it.
See how R3 is still 3? Or registered 3? It still stores 3.
You are correct.
Yeah, that's what I was saying. It's like the R is voided. So it doesn't matter what value you set for R. That's why I was kind of confusing the.
Yeah, because if you look, let me see where we store out for R.
I think what we meant to do was like do the P minus Q and then store that as R, right? And then we're gonna debate whether we add to if it's positive or negative or equal to 0, right?
Then you have to set in that case, if you wanted to do it that way, you have to set another location to have the
To take the
output
R number.
from, yeah.
Yeah.
Then you have to set it. I was trying to save a step by kind of like the last one where we would use the Z. But yes, you are correct, because if we wanted to use this as a result, we should store it as a result, and then we can use that to check to branch.
Yeah, to debate
Right.
whether we add to,
Right.
right?
So that
'cause
will be
I
a
like
better
this.
program. Yeah. So what you would do is you would have RES as the result, store that out so you have the return result, then you can have it branches, right? Because here we did branch it that way, okay? So we can branch it to positive, and instead of adding 3 to it, I think that's what we did, right? Let me see. +1. Yeah, so instead of +1 and or add 1, add 2, add 3, what you can do is you can tell it to, like the other one, you can tell it to display 1, 2, and 3 in the case where it's positive, negative, and 0. Okay. So I'm fine with you testing it and showing the result. That will be okay.
Oh, and then one last question. Can you show how to input the negative hex numbers? Because I just did it like in decimal form when I plugged in the set values.
Okay, let me reinitialize. Load the program. Okay. Let's do so you're trying to do it like this, -4. Is that like that? Or hex -4?
Yeah.
Okay. And then 3101 or 3201, let's say that we put hex -5. Okay, so let's jump to it. Yep. That is the negative value there. So when you put in a negative sign, it converts it for you.
Oh, so you can still put the hex number, you just have to put the negative after the X. It doesn't come before it.
Yep.
Oh, okay.
Yeah, because if you put the sign before, it doesn't know. And you can use decimal too, right? So let's say, see how when I put in the negative, it converts it for me. But if I put in like a decimal, right? -3 like this. See how it didn't like that? So for input, we always wanted to use the hex, and then you can follow it by the negative sign like that. Then it will be able to convert it. Because if it doesn't throw you the error after you set it, then it's not, you know. But with this is, see how it shows that it's also a trap? Okay. So it's going to use trap, and then whatever that value is, it's going to trap at that vector. So when you use a negative input, you are actually setting up a trap with the value as its vector. So if I use like a negative hex 4, right, then it's going to trap at vector 4 or FC and then FB. Okay.
So if you run that, it'll be -9, right? In R3.
At hex, what is it, 3002? Well, I need to fix it because either way, right, it's still going to retain the 3 from the last one. But yeah, It should, if you wanted just to output. So -4 minus -5, and you can also check on your calculator. So if I have hex, right, -4 plus hex -5, that's going to be equal to that. Let me do that again. So when we negate that, we see that it's FC, right? And then we're going to plus, yeah, should be FFF7, which is -9 in decimal. You are correct. It's 9 in decimal, but in hex, it's going to show you the hex value. So make sure you check the hex value. And be careful with the negative though, because you should treat it as 2 complement, because when you are using sign value like that, remember that it's using this, it's larger than 5 bits. So it's not going to be able to show you based on the limitation of your program that you didn't allocate the space to really, you didn't include the appropriate step to really show the output like this. Because when we negate the 4, you saw, right? Like when you do a hex negative hex 4, it's actually FC. So FC is 8 bits. 8 bits is larger than the 5 bits immediate value. So it's not going to give you the right output if you test it with the negative. Now, if you want to fix the program to make it where it would give you the appropriate negative hex output, you got to make sure that you would allocate it in the subtraction, right? As we would have to make sure that it fits the space of the 8 bits. Because the limitation for our program, the way that we wrote it, is it's only going to handle the small number. 1 digit up to 5 bits. So that would give us 1 digit of hex. Anything above 1 digit of hex, it's not going to do. So what you can do is you can think about how you would be able to add in the sign extended by using the 2 complement and then convert it. Let me think about that. -4. Yeah, so if we're trying to do an input like that, we might have to check the input for P and Q. Because with this, that's just going to be, if we're using the register the way we have, it's just going to be it's going to be 0 through 9 for the decimal and less than 5 bits. Okay. Maybe you can load it instead of add it. So I would do that instead of add if you wanted to use negative hexadecimal. So it treats it like an offset. No, you're the first to ask about that. I don't think any of my students have actually thought about that before, and that's pretty good. Okay, because I didn't even think that I should test it with the negative hex value. But when you test it with the negative hex value, you do see that there's limitation with it.
Yeah, that's
So,
all. Yeah, because I spent
yeah.
a lot of time trying the code out, and
So, but yeah, so I think what in such case, if you wanted to use negative hex value, then we should think about the operation, right? Like instead of adding the value and store it out, maybe we should think about how we would load it instead. So that way it treats it like a loaded base offset instead of an actual data number, you know? Let me play with that. I have to work on that and see how it's gonna affect the rest with the way it branches. And then I'll let you know. Because we can probably tweak it. It's doable. It's gonna change the structure of our program a little bit. And then you can play with it and let me know what how you solve it. Okay. So, I mean, a working program doesn't mean that it doesn't have limitation, right? A working program sometime, all program has limitation. So, it's good that we see that and then we try to work about that. So, okay. All right. Anything else? So for number 3, let's see, I'm at 8 o'clock already. But for number 3, if you don't get to finish it, it's fine. But if you try to finish it, I like for you to attempt it. And you know, if you haven't turned it in, you can still turn in your lab and then I'll update your grade. All right, type your name into the chat. I'll stick around for a few minutes in case you have questions individually. Have a good week. Don't forget, no live Zoom on Thursday. Enjoy your week and try to do the lab. Email me if you have questions. I will be available next week for office hours and regular sessions. Okay, so see you next Tuesday.
All right, see ya. Thanks.
Hi, you're welcome. Thank you.
Oh, yeah. I know you said there will be no Zoom meeting on Thursday, but would it be like a pre-recorded lecture? Or...
Yes, I will have my video posted tonight.
All right, then. Thank you.
You're welcome. Anything? Good night. If you don't have any questions. Good night. Excuse me, any questions? Okay, so I'm gonna sign off. Nadja, Beethoven have no questions? That's okay. All right, thank you. Good night.